Welcome to Yaka Digital Network. When you look at a digital map of Kampala, you might wonder how the system knows exactly how to move a boda across your screen, or how structural engineers calculate the stress on the buildings down there. The answer lies in matrix transformations. To shift an object on a grid, we use a simple formula. The image, the new location, equals the transformation matrix multiplied by the object's original position. To make this math work, coordinate pairs, like 3, 2, must be stacked vertically into what we call a column vector. Before we move anything, we have to establish a mathematical home base. This is the identity matrix. If you multiply any coordinate vector by this specific matrix, the math runs, but the object stays exactly where it is. It produces zero movement. In modern digital design and engineering, matrices serve as active operators. By changing the numbers inside the matrix, we exert force on the coordinate plane, dictating exactly how objects scale, spin, and slide. Let's apply an enlargement matrix with a scale factor of 2 to a simple triangle. We start by placing one of the triangle's coordinate vectors next to our operator. To find the new coordinate, we use the row by column method. First, multiply the top row of the matrix by the column vector to get your new x-coordinate. Then repeat the process with the bottom row against the column vector to find the new y-coordinate. Once calculated for all 3 points, the geometric effect becomes visible. The triangle expands outward, and that scale factor of 2 means its distance from the origin has exactly doubled. As you set up these equations, there is a strict rule for operator order. You must always write the transformation matrix first, multiplied by the point vector, never the reverse. Because of the strict rules of matrix dimensions, flipping this order literally breaks the calculation. The rows and columns will not align, and the mathematical engine fails to start. Now let's test this with a y-axis reflection. The matrix for this is -1, 0, 0, 1. Pause the video here, set up the equation for point A at 4, 3, and calculate its new location. When you multiply the row by the column, the -1 flips the sign of the x-coordinate, giving -4, 3. Watch the grid. Point A jumps directly across the y-axis, acting exactly like a mirror reflection. Let's look at a more complex operator, the shear transformation. Geometrically, a shear matrix shifts the top corners of a shape sideways while keeping the base entirely anchored in place. Think of a stack of heavy textbooks on a desk. If you push horizontally against the top book, the whole stack slants sideways, but the bottom book stays put. A shear matrix applies this exact same slanting motion directly to coordinate points on the Cartesian plane. Structural engineers in Uganda rely on this exact transformation to calculate how high-rise buildings will respond to and withstand lateral forces, like heavy winds hitting the top floors. Up until now, we've used a matrix to transform a single vector. However, the same row by column logic applies when we combine transformations. If you multiply a rotation matrix by a reflection matrix, you get one master matrix that stores both instructions, allowing you to perform complex sequences with a single calculation. This table summarizes the standard matrices you need to know. Take a screenshot right now. These specific arrangements of ones, -1s, and zeros form the permanent rule set for controlling geometry. Mastering these simple rows and columns provides the rule set for digital and physical design. Whether you are shifting a character in a game or calculating the slant of a building, you are using matrices to define the geometry of the coordinate plane. Thank you for learning with Yaka Digital Network. For more classes, detailed notes, and interactive content, visit us online at www.yaka.cc.